The Haiti earthquake hit in 2010, and I was there 2 days after. And World Bank picked me up, and they asked me to assess about 50 different governmental buildings right after that. The earthquake is horrible, killed almost 300,000 people, and I've damaged about 200,000 buildings. It's really, things that happened here was bad, but it was nothing compared to what happened in Haiti, actually. So I stayed there for 2 years, and we trained about 600 Haitian engineers and about 6,000 masons. And with the USAID funded and Red Cross and so on, we assessed about 430,000 buildings and repaired about 20,000 buildings out there. And so that's what I do for a living, you know. And by the same time, I get involved in different things. For example, here, issues are very different from what I saw in Haiti or Japan. Issue is, it's more finance, more economy, more the real estate components. After all, yes, Christchurch earthquake was bad. We lost almost 200 people. But 200 people out of 350,000 people, the performance was actually, believe it or not, in a building code point of view, it actually met intent of code, you know. But however, how society reacted to it is very unique, I thought. And it's very unique that how much insurance you had, now you don't have much anymore, and it's really causing a lot of confusions here. It's kind of a, well, I don't say interesting, but it's a very unique condition. I gotta drink water. So, last 30 years, myself and partners, we visited almost 100 different earthquakes, from Japanese one to Asia to just Americas, just you name it. And the reason we do that is not only we train people assess damage, but also we collect the data. We collect the how the buildings behave, how the actually seismic hazard, how seismic vulnerability in the buildings, and how we can control the risk. That is the one of the main reasons we at disaster sites. And having that, we developed a database. Database basically tells us what realistically what's going to happen to the building. And that's actually really important. Here's a picture of a Christchurch right before the earthquake. This is today. You know, we lost a city there, essentially. Let me show you one example. This is a 26-story hotel, refurbished in 1995. And you kind of see that the little kink in the building, because 2 columns ruptured at the 11th level. No one died. Guess what? This is total loss, but this met the intent of a building code, 100% of NBS. Because intent of a building code is life safety only. It's nothing to do with the preserve the buildings or functions or anything like that. So that's the intent of a code here in New Zealand and California and Japan, everywhere. So whatever you design or build for 100% NBS, you're going to see this. Now, what is the 100% of a building code means anyway? Well, that's why I said life safety. But I know it's interesting things going on. If you ask 5 engineers, chances you're going to get something between 5% to 150%. You know that. Why is that? Well, let me tell you why. Building code is not really meant to be to use and gauge the capacity of existing buildings. I don't know how to do it. Building code is meant to be for new construction. The seismic behavior, or buildings behavior under seismic motions are really complex. Let's say if I try to analyze this building, if I have a humongous 2 supercomputers and have a best software, I'd probably be off by maybe 30 to 50% to forecast. But building code is something try to deduce this really complex behavior to something very simple, That's what building code is. It's true in Japan and California too. So try to use the, in a sense, cookbook to analyze, evaluate, strengthen existing buildings is difficult. Let me give you one example. So we have an office in Christchurch and here in Auckland, but Christchurch, we have decided to buy this office building. 3-story, it's about the 600 square meter. I think the building was 1970s, look like. It's in a CBD, was in the red zone, and it went through the earthquake, yellow tagged. Some damage, not much. Slab on grade, got bubbled up a little bit. No settlement. I saw some cracks, it's not bad. Building performing well. Considering the Christchurch earthquake was almost 150 to 200% of the so-called design earthquake. It seems to met the intent of 100% of the code, right? So I asked our engineers, my engineer, our guys, because it's going to be our building, to do the assessment. And he came back to me and said, this is probably about 25% of MBS. I said, well, how can it be? The Mother Nature tests this building for about 150% of the building code and did not damage. And he just said, well, because we follow the building code is essentially what we call static procedure, static elastic procedure. And he said, well, because static procedure is conservative. I said, well, what are you going to do? He said, well, we're going to check against displacement-based approach, which is in a part of the code. So he used this advanced displacement-based methodology. It went up to about 100%. But you know what? Even 100% or higher, it's computer simulation shows that. It means nothing. We don't know what we don't know, Engineers, we don't know what we're talking about, quite frankly, We are always wrong. Every single seismologist, every single engineers, we are always wrong to this today, right? So for that building, what we're doing is, yes, we satisfy the code thing, and we satisfied our feeling of how this building is tested. But what if the magnitude 7.5 rupture nearby, and now the duration is a 30 seconds motion rather than 5 seconds of a stronger motion? I don't know what's going to happen to it. So we decided to provide some little dampers on the front of it. It's very cost effective, about $40,000, $50,000 of it. Because I don't know what I don't know, So that's very important. I think it's important the fact that understanding the building code is a simplified method and tend to become really conservative using the simplified way. And using the advanced methodologies, which is per New Zealand code, usually you can get a higher MBS. But even when you do that, I think you was on a question to engineers like me, do you know what you don't know? Japanese engineers, they said that the maximum tsunami height in Tohoku coast is 10 meters. So they designed a big tsunami wall for 10 meter high, actually about 11 meters, somewhere on there. Safety factor 10% or something, right? They built the Fukushima nuclear plant, and you know what they did? They put an emergency generator, which is the most important, one of the probably most important thing in a nuclear plant, in a basement. So of course the tsunami is about 15 meter high, or about 20 meters, something there. Went over it, drenched the basement, and we have a nuclear meltdown. Can you imagine how arrogant we are? If we say maybe we don't know what we don't know, and we maybe spend a couple $1 million to put that generator on top of the some frame, the Fukushima plant is something you don't know because it never become news. You see? So that's something that we should be always think about it. So seismic management, risk management. We have essentially 3 different options. Well, number one is do nothing option, which we can do that for 15 more years actually. Because the government said that we have 15 years to deal with it. Option 2, buy the insurance, which is essentially what we did prior to the earthquake. Because insurance is really cheap, really available, a lot of capacity, and it really made sense. Option 3 is reduce the risk by the engineering and the construction, seismic strengthening essentially. The right option is actually combination of both, actually all 1 and 2 and 3. Those are very important to look the portfolio. Sometimes do nothing actually makes sense, believe it or not. And sometimes the buying insurance makes sense. Sometimes the reduce and strengthen makes sense. And it's all balancing act because we have a limited resources. Give you one example, do nothing options may be possible option. We've been asked by the World Bank to look into the city of Manila, Philippines. They have this fault called West Valley Fault. You cannot believe how dangerous the thing is. Just zip through the city. And that city, they never even thought about seismic hazard there. And they built the concrete structures, non-ductile concrete structures, just unbelievable risky place. And they have about 4,000 schools and 20 hospitals. And they have about $400 million. Seems a lot of money, but it's not for 4,000 schools. About 2 million students there. And then we did all the risk study right now, and we come up to about 20,000 students we're going to lose, most likely, once the 7.2 ruptures happens. What we're going to do, $400 million, 20,000 students, 2 million students affected. Well, we did a risk study to prioritize the assets. Limited amount of money, how we can actually reduce the overall risk of a portfolio. In this case, is how many students we can save, you know? So some cases, we cannot fix it. But spending certain money in certain schools could save more lives. It sounds harsh, you know, but that's the fact of life. But doing something is critically important. Because I think problem is that in many cases, limited amount of money, people don't do anything. And that actually causes an unbelievable dangerous condition. You actually touched that, you know. We got to do something, and do now is so much better than do 3 years from now or 10 years from now. It's a life we're talking about. So give you some certain examples here, and one, this from JLL of this commercial components of it. Average in Wellington here in office market, if you have a building that meets 100% of MBS, average rental is about $300 per square meters. If it's less than 33%, it's $160 per square meters. And I bet you this is actually going down. This is probably no one's gonna really, quite frankly, will not and probably should not occupy the building, in my opinion. And almost 80% of tenants want a building with a 67% or higher MBS. And the large firms and the government entities is requiring is 67%. So yes, government requirement may be 33%, but actually market basically tell us that 67% is a standard for commercial sector and the governmental sector. Now, good question, you talk about 33%, 67%, how much is cost difference here? We probably did the seismic strengthening, I don't know, 1,000 cases, many different places. The difference is not much, quite frankly. You know, 3 boats or 6 boats. Because most of the costs are really when you go into the building, disturb the architectural elements or mechanical stuff, that's actually a lot of cost to it. So adding a few more things into the structural system is not that much expensive. So that's something that I think there's a myth out there from doing it at 34% the way to go. It's not. It's going to be about similar amount of cost. In safety factor, safety to life does goes up as that go up to the higher values. I'll give you a few case studies. Heritage buildings in Christchurch. This is a little church in a Christchurch, went through the earthquake. Little damage, not much. And engineered the assessment, come up to about 3% of MBS. Again, this building went through the 150% of MBS seismic motion, you know, and no damage. It's kind of weird, isn't it? How can it be 3%? 3% more like if you can push it, you can push down. You know what I mean? It's an old building, built in 1930s and 60s. small concrete. But one thing we noticed is a reinforced concrete building. So what we did is that we used the advanced method to really check the capacity of an existing concrete, which does not meet the modern code, but it's concrete and the rebar has certain strength in there. And our job to capture why the building behaved so good under this big earthquake, that's our job, right? That's what we did. So when we did that, it suddenly became 120% of MBS. I think that's maybe the difference between, you're going to see the different engineers give you different numbers. Some may use the simplified methodologies, some may use the advanced, more thought through, displacement-based type of approach. Maybe that's the difference is. So, and they spent about $80,000 for repairing, and this went through the SERA, which is actually, it was not very pleasant experience, but we went through it anyway. And we got approval. And December 2011, I think it was a Christmas Eve or 23rd, we were able to open that church. It was cool, because it was a heritage building, and the Christchurch lost so many heritage buildings. It was bad, Heritage buildings are important. It's the history and the culture of the place and the people. I think we really should save much as possible, and there are cost-effective ways to doing that. Small commercial buildings in Napier, 2-story, kind of ugly, 300 square meter, typical, building. But the story here is in a 2-month time, this bank, it was going to leave this premise because it was earthquake prone, and they can only occupy it only 67% and higher. So seismic systems is a typical one, combination of different things, concrete, brick, you name it, wood, everything. So you can see the kind of very standard commercial retail setups. So we went in there, we did a few things, put some braces in. This is, you're looking from outside, storefront, you can see that little brace we put it in. Looking from backside. I don't know about you, but I think it looks really nice, It's cool. It is. It's kind of architecturally, it's much enhanced now, And this is actually a very important detail. This sounds a little bit silly, but I want to show it to you. This is this got the brick wall. And brick wall, most of the heritage buildings actually perform fairly decent, exception of a church though. Church is actually pretty dangerous buildings because so big, and so many of the commercial heritage buildings perform very well. Many actually perform well in Christchurch. But what didn't perform well is a facade. The brick wall fall off. That's how many people died from it, about 40, 50 people. That can be restrained by this little bolt detail you're looking there. That's what we call out-of-plane anchorage. This is so important. Now, I think one of the most successful seismic strengthening programs adopted last 30 years is California's out-of-plane ordinance. What it is in California, we put the ordinance that about 10 years' time, every owner, commercial and the public owners of the heritage brick buildings have to use this detail, put bolts in it. Is that a perfect thing? No. But it reduces the risk tremendously. That's the point. And this is so cheap. In 10 years' time, the tenants in and out, empty, just put some bolts in there, put some strap in there. It's cheaper than a carpet. But this saved lives. This saved lives, and this is extremely, extremely effective. So today, about 95% of our URM buildings in California have this, And it was commercially feasible, and we really put emphasize having this type of buildings is not only commercially feasible, but market value goes up, and tenants should be in this kind of buildings, and that's how we communicate with publics there. So back to Napier, we spent about $94,000, which ended up to about $260 per square meters, and it was 11% MBS, went up 95% MBS. See, requirement was a 67% MBS, but it's not like we're going to shoot for 68%. We just put some stuff in there and just naturally goes up, and that's what And this was done in a 3-month duration because that was the timeline was so tight we need to do it. Today, many of buildings like this, people vacate it. Tenants are leaving. The owners losing their lifetime assets. And some of our heritage buildings like this one is actually people taking down. There's no need to do that at all. $260 per square meters makes sense. We should do this today, not 15 years from now. And this will save lives and save the assets. And also the owner can make a lot of money doing this. Not only he was able to retain a bank tenant, upstairs was vacant for a little while. Now he has the people lined up to get this space now. You know? Mid-rise office building, Christchurch Red Zone. I like the title, sounds kind of intense. So here's a 6-story building. And again, this building went through with no structural damage at all. Some little cracks here and there, but it's not much. And this is, I think, engineered and built by Public Works, what's it called? Ministry of Works. Looks like it. Yeah. There's a lot of concrete in there, man. It's strong, But unfortunately, again, if you run MBS, it gets you like a 33% or 33.2% or something like that, some of nature. And so there, what we're gonna do is, this building, and many of this kind of concrete building has issues because the core is in a sense, providing the stability of a seismic motion, kind of like a spine in your body. And if this spine in your body is right on center, actually works pretty good. But you can see this kind of offset out there. So that will cause a lot of torsional movement. And that's something not really good for the buildings. So what we did here is we actually made it work for over 34% of our building code. So in theory, this owner don't have to do anything, but we made a recommendation to, hey, let's put some cool things in there. You see that little red thing? That is the seismic damping devices. So that reduces the torsional excitation. It's made by the company called Taylor Devices in New York, Buffalo. And there's actually several manufacturers like that make this damp. It's a shock absorbing device. It's mainly developed for the aerospace and the military applications. And concept is the exact same as your car. You have a spring, you have a shock absorber. Just imagine your car did not have that shock absorber. You're going to bounce, And same concept for this shock absorbing device. Every presentation has to have moving pictures, in my opinion. You see? Now, is this correct? Not really. It gives you tendency of it. So having dampers definitely reduce the excitation, reduce the movement of a structure. It would cost him about $200,000 to put it in there, or somewhere in there, $300,000, I don't remember, for this shock absorbing device. But it so makes sense. It makes sense not only just the minimum meeting the code, but doing an extra little bit. It gives you a higher safety factor for life savings, and it's not only affordable. This actually, he's going to make this as the kind of marketing focus. So here's what it looked like. See? Shock absorber could be nice. The structural engineering could be sexy. You see that? Yeah. It's beautiful. And we use the things called FRP also. This fiber reinforced plastic, and some of buildings here are being used FRP also. This is essentially plastic you can, in a way, glue to the concrete or masonry to add a strength.
One of the things we've seen that you should do is make the strengthening obvious. Mm-hmm. If you bury it behind the facade, people don't know you've done it.
I agree 100%. Yeah, actually, this owner definitely, that's one of the main requirements to his architect, There are many architects nowadays, they do want to expose those strengthening elements, which I think is a good idea. Are there any architects in this crowd? Don't you think? Yeah. It's a good thing I didn't make an architectural joke here. But yeah, I mean, exposing strengthened elements is very important, you know. And that's that also create the commercial value in this country. So now I'd like to talk about a little bit about portfolio management, because I know some of you do look at the major portfolio and how we're going to manage it. It could be applied that to the campus of a school. It could be applied to 4,000 buildings in Manila. It could apply to the 400 assets in Wellington. So this is just an example of it. So here's the one example showing the 5 buildings, showing the building types. And in many cases, well, this country, we use percentage MBS to show that, so-called triage, like you said. But percentage MBS do not give me anything at all. I guess if it's less than 33%, I just kind of think about it, you know. But it really, I don't know how to use percentage of NBS, quite frankly. I cannot judge the buildings are good or bad based on percentage of NBS. And I have a PhD in earthquake structural engineering, you know. I can't, I just can't. So what I do, we use a probable maximal loss. And this is a database I was talking about, what we developed over the years. Probable maximal loss is the essentially what would be a potential, we do this, displacement of building by the earthquake, and what displacement caused certain damage, and what is the financial loss percentage based on the replacement cost, or sometimes we use a repair cost. That's what we call PML, probable maximal loss. And then we use this form in different clients. For PML, probable maximal loss, we use for commercial sectors because they're looking for the financial risk. Insurance industry, PML. Last thing you want to send to your insurance people, percentage of MBS. They will get confused. You don't want to do that. They need a PML. That's the information they need. Place like Manila, you know what we did? We did a PMD, probable maximum death. You know, it's a harsh, but that's what it is. So we get the PML, rank them, 20%, 50%, 50, 32. Now I have some certain understanding of the building performance now. And in this case, CFO is our client. He's looking at the potential financial loss, you can see. And business interruption potential, which we figured out based on the building movement, displacement, or damage. Building A has about 3 to 4 weeks of a business interruption. Building B has a 6 months of a business interruption. Let's pick the building A. It had about 20% of the financial loss factor. And it's a steel frame structure, and usually steel buildings perform good, as you know. So it kind of makes sense. And the business interruption potential was about 3 to 4 weeks. So this particular case, we decided to do nothing to this building A. Building B, it's opposite. It's actually newer construction, but PML of over 50%, which means almost collapsing. And business interruption potential is over 6 months. And happened to be these buildings are very important for this campus. So decided to do something about it. You see? Now, this is how you can prioritize the whole assets, essentially. If I say, let's fix everything for 67% of MBS for all those buildings, you can't afford it. You know, that's not how to do it. Give you one example how we screwed up in California. We passed an ordinance called SB 1953. And we said that all the hospitals in California, both private and public, has to meet 100% of a code in 2000. I think the first time deadline was 8. Of course, no one can afford doing things like that, especially in hospitals in California. You know, they're not making much money at all. So they couldn't afford it. So guess what? Due date pushed to 2013, which passed. Now passed to 2020. I bet you kids can keep pushing ever, because couldn't afford it. You see, try to do certain things for everything for portfolio, end up to creating a much higher risk than anything else. So California, we don't have very safe hospitals. That's one of the failures we have. Cost benefit. So after we go through the prioritization of it, next step is the cost benefit. which means how much should we fix it? Should we fix to what level? So again, here we looked at PML. So building B, the first new column, you see it was a 50% PML, which means a high damage. And if you spend about $230,000, the PML will be reduced from 50% to 25%. But if you spend about twice more, $430,000, PML goes down from 50 to 15. This case, the owner decided to do option 1, and he bought insurance to transfer that remainder to the insurance industry. So that's how he managed the risk, from reducing risk and buying insurance. Now, insurance companies, they really like this. This proactive seismic risk reduction program like this, something you can impact the premium. I have no doubt in my mind if you communicate correctly. And I do go to London quite a bit and talk to many underwriters. Some cases they ask me to talk, what's going on in the world. And that's something they're looking for, 2 things from the commercial sector. One is correct, right data in the right amount, not too much. They're looking for building types, not done by the broker, but done by the engineers, and also PML. They also run their own model too. They get their own PML, but they want to see how local engineers see it. So that too, and then the commercial sector, who's actually managing the risk, because obviously, if you manage the risk, so therefore their loss can be managed. You know what I mean? Okay, here's one example on the LA. This campus is $1.3 billion. Now partner Peter Yanev did a seismic strengthening 2 years before the Northridge earthquake event. So this is actually pretty interesting. Actually, we did it, went through the earthquake, and how it actually performed. This campus is about $1.3 billion, so it's a big asset, and right at the Northridge, and built in 1954. And give you one example of this. So we went through the portfolio assessment of the prioritizations and cost-benefit analysis, and we picked several buildings to strengthen it. This one example here, looking here, one in the left is a before, one in the right is after. You can kind of see a slight difference in 2 different pictures. One is lost few windows. Actually, he put the shear walls on the backside. And this is obviously done during the operation. So seismic strengthening can be done. It can be subtle to make a big difference here. By the way, this building is a brewery, and this is the Budweiser campus at the time. So it's very important place. Well, people in LA and in California in general, but here too. So it results like this. Business interruption was only 4 days. And 2 years before, the owner spent about $10 million for seismic strengthening for this $1.3 billion set. And they estimated, their risk manager estimated, avoided damage is about $350 million. Avoided business interruption was $400 million. And also they avoided market share loss. So they estimated about $1 billion of a so-called net gain, spending $10 million. Just think about it. For the commercial sense, really makes sense. I was going to say something. What was it? I'll come back, I'm sure. Last slide here. So conclusions. Now, I'm talking about financial driven like this, but remember, when we're doing this thing, we're saving lives, I think that's the most important gauge, saving lives. But to do this, we need to be commercially feasible to doing it. And that's one thing I know. And that is extremely critical fact. Commercially feasible way. So balance the risk transfer by the insurance and risk reduction by the engineering. And use advanced method for retrofit, not just following the simplified building code. And because that's going to give you the cost effectiveness and realistic engineering measures. And doing this, you can convert a distressed asset to something successful, just like what you saw in Napier. just what you see in Christchurch. It's definitely possible and feasible. So yes, there's a lot of fear in the market, a lot of fear in society about what's going on here and what's going to happen. I don't think it's a big deal. This is being done in many different places, and you get probably one of the best engineers in the world. After all, the New Zealand engineers invented a base isolation, and which is probably the best form of seismic engineering. We used in Japan for about 5,000 different locations, but it's all come from here. So it's definitely, we have a capacity here to doing this. But I think we need to communicate correctly, and just not only use the engineering, but use the both commercial sense, because that will end up to saving lives, and that is so important. Our mission is critical. Thank you very much.